Real-Time Operating Systems Part 4. I'll be talking about the minimum features that are necessary for an RTOS. And I was going to get to the differences between an RTOS and a scheduler. Again, I'm going to defer that to the next time. And as I always say, go to ragingdisk.org, follow the links over to the Bitbucket Git repository for NUFR and the Raging distribution. Go download that, try it out, and you'll get to learn everything that I present here. You've got everything you need in that repository. Make system, all free tools. You can get yourself a reference board from ST Micro or a TI MSP 430, and you can get an example program up and running in a short amount of time. It's full of documentation. Take advantage of it. It's a great way to learn an RTOS. Completely open source. Now, what are the capabilities that an RTOS needs? Well, obviously, it has to be able to run hard real time, and I covered this in a previous part to this series. The RTOS itself has to have that capability, but if a system's going to run in real time, you can't have junk for drivers. You've got to have your drivers written to run in real time. Just having an RTOS that can run in real time can be defeated if you don't have the right code, including applications and drivers. But an RTOS can't run without the hardware to support it. It can't run in real time, that is. And most hardware is real time capable, but sometimes you run across the occasional file system, disk I/O, whatever. File system is going to be in the firmware. But you might run across a piece of hardware that's not capable of real time because it does some buffering or something like that. But even on something like a PC, that's unusual. But it's still a constraint. Now, the principal job of an RTOS is to allow threads to be run and to manage these threads. So an RTOS must have some basic threading capabilities. A thread, of course, has to be launchable, and it has to be paused at some point to allow another thread to run. If you have a thread which can't pause, that means you can't switch to another thread, and you cannot meet your real-time deadlines. And the terminatable is actually optional. I think it's a nice feature to have, but it's really not used very much. So a thread, when I say a thread, and again, I've covered this in a previous part of this series, a thread can be a task, and a task is the main thread, say, housing unit that a RTOS has. And in larger systems, the larger operating systems, memory management systems, these are processes. So threads can be a process with a single thread. They can be a p-thread, which in other words a process with multiple threads. P-thread is a POSIX creation or something like that. And but we will focus on the tasks only of the RTOS, because an RTOS is simpler than a more sophisticated system like Linux or Windows. System RTOS, operating system. Linux and Windows aren't real-time operating systems, of course, but there are real-time operating systems out there that use processes and not tasks. That distinction is beyond the scope of this discussion. But a task is a thread, and it is a thread that the RTOS will manage. And we talk about tasks, and when we talk about RTOSs and applications that run on them, we usually talk about tasks and not about threads. Threads is more of a conceptualization. When you get to the nuts and bolts, you're going to say this task, that task, and the word thread doesn't come up much. But an RTOS must be able to manage several tasks at one time concurrently. And an RTOS task is that thread of execution and everything that surrounds that thread that's needed to support it. So that's the surrounding parts we call a context, and that's it. Now in a process, you've got things that they say something like Linux has to do with file handles, and has to do with spawning other processes, environment variables, and all these nice extras that tasks don't do. And that's why they're called a task and not a process, because they don't do everything that a process does. But an RTOS must support multi-threading or multitasking. And RTOS, which has several threads, it doesn't do any good if you can't switch from one of those tasks to the other. Of course, I'm talking about a CPU that is not a multi-core, and usually RTOSs run on CPUs which are not multi-core. Not to say they couldn't run on a multi-core one up to a point, but that's a different discussion again. But the ability to switch from one task to another is probably the most important job that an RTOS does. And RTOSs provide support. They provide objects and all sorts of things to facilitate that switching. So a context switch is when the RTOS switches out one task for another. And also with a thread is, you could throw in an interrupt handler, an ISR or something, and the category of thread would cover tasks and ISRs, because an ISR is not a thread. But a task must be suspendable right at an assembly language boundary. So this is the way the hardware works. When the hardware interrupt happens, and this is what drives a context switch, it will complete the current assembly language instruction, machine instruction, that the CPU is doing, and then bang, it will call an ISR, and the task must be able to stop on that assembly language instruction and then pick up at the next assembler instruction. So the RTOS must save everything in what we call the context, which I covered last time. It must save everything in order to pull that off. And it must restore everything to make it look like this whole thing was just a delay in time, a switching from one task to another, then back again. Now, there is something I call a direct context switch, direct context switching, and I'll get into this in a few slides. But a direct context switch, by my definition, is a short, efficient path which does the following. It saves the context of the task being switched out, restores the context of the task being switched in, and it updates some kernel state variables to keep track of what's current task which is running. And it does all this atomically, and I should say it does it quickly, and it does nothing more. So atomically means that once you enter the kernel to start this process, it won't interrupt the kernel to start another context switch. It will complete this one thing before it goes on to do the next thing as far as the kernel is concerned. So if you don't have these capabilities, you are not an RTOS. Direct context switching rules out a lot of things that schedulers and other pseudo-type tasking environments will do. Multitasking needs the support of these parameters. It needs the priorities given to the task. So every task must have a priority number, and that number determines, when you have two tasks running, which one gets the CPU. And again, like I said, single core CPU. So along with task priorities, you have the concept of preemption. If you have a task which is assigned a higher priority, and by the way, usually a lower priority number is a higher priority task. So say a priority of 0, 1, or whatever the system supports as the lowest is going to be a higher priority than 10 or 11 or 12. But task preemption means that if you have a task at a priority of 5, which is running, and one at a priority of 4, which wants to run, it will preempt the task at a priority of 5. Another aspect of multitasking, so preemption is essential. All RTOSs must have the preemption capability, or they're not an RTOS, because without preemption, you cannot have applications meet the real-time deadlines that systems demand. Now the round-robin capability of the task scheduling is a nice to have. I'll talk about round-robin scheduling in a bit. Our RTOSs do not have to have round-robin, but I think it's important. It's an important feature, but it will not disqualify an RTOS from meeting real-time deadlines. So back to task priorities. These priorities can be assigned. If you don't have round robin, each task has to have a unique relative task priority. If you have round robin's capabilities, then multiple tasks can share the same priority numbers. So if you've got, say, 20 tasks in a system, then if you don't allow round robin, then you have to have a minimum of 20 different priority numbers assigned to these tasks. The numbers don't necessarily have to be contiguous, and this will vary from RTOS to RTOS, but they have to be unique. Of course, if you have round robin, you can share the same priority with all the different tasks. Some operating systems only support round robin multitasking and don't support preemption. Now, they are not real RTOSs. They are not real-time capable, just supporting round robin. But this sort of design, this sort of architecture actually is more common than you would imagine, having round robin. I believe the early versions of Windows, Windows 3X, was a round robin only. Not sure about that, but that's what I understood at the time. So preemptive multitasking will always allow the higher priority task to run if it is scheduled to run, if it's informed the kernel that it wants to run. Now when you start using objects that an RTOS has, then you find problems if, let's say, with contention with a mutex and things like that. But that's a case where a particular high priority task is not allowed to be scheduled. So I'm talking about the step from when a task is scheduled and what the kernel does when it's at the highest priority. So whenever a higher priority task takes the CPU from a lower priority task, this is the concept of preemption. Round robin multitasking is an algorithm of a sort which the tasks of the same priority share the CPU. The round robin algorithm allows tasks to get queued up that are wanting to be scheduled by the CPU, that are not blocked, and these concepts I'll explain later. And by the way, all these concepts, and if you look at the NUFR user manual, you'll find good explanations for these terms that I use, and just good explanations for any RTOS in general. These terms are used throughout the industry. There's slight variations from company to company, and from book writer to book writer, and the concept might have a different name, but good explanations out there. Go download that manual even if you don't stand up the applications and everything. So the round robin algorithm works by having all the tasks of the same priority get queued up in the order in which they have gotten queued up, or they have requested the CPU from the kernel. That is the order which they'll execute. And whenever they get blocked, if they get unblocked, then they got to go to the end of the queue. And whenever you have a round robin scheduling algorithm like this, the application developers must be cognizant of the fact that they have to give up the CPU from time to time, or the other task will never run. This, of course, is true of a preemptive multitasking scheme also. If you have a high priority task which never yields a CPU, guess what? The other tasks won't run. You've got something similar here with round robin, except that it's usually with the high priority tasks, though it's not a problem, because you know that this thing's gonna suck up the CPU, and so when you write the code, you're careful not to have it hog the CPU. But when you get into round robining, you don't always, the application developer doesn't always think about this. But nevertheless, on any working system, all these tasks which run at the same round robin priority all have to be what I call gentlemen. They have to yield the CPU so other tasks can run. Now, I've thrown exceptions into the category of threads. So you've got tasks and you've got exceptions. Let's talk about exceptions for a while, because this is an important part of RTOSs. And a lot of the literature on RTOSs just talk about tasks, and they put exceptions on a back burner. But exceptions are extremely important in an RTOS environment. What is an exception? And I'll continue to say that I cover this in other parts of the series. They are a broader category of hardware interrupts and software interrupts. So hardware interrupts and software interrupts together form the class of exceptions. Some smaller CPUs just call these things interrupts. It's according to the CPU maker. They will label these things as one thing or another. They might just say interrupts. If it's a little CPU, they won't even use the term exceptions. And software interrupts go by different names. In some systems, a software interrupt which is called from an application instruction might be called a trap. I believe that's on the 68000 code. And there are other software interrupts. So it's besides traps, and by the way, traps are usually the means on a lot of OSs, RTOSs and non-RTOSs, whereby the user space makes a kernel invocation. It makes a kernel API call, basically. So under the covers of, let's say a Linux API call, you will find a trap or a software interrupt of some sort, depending on the CPU type. The other types of software interrupts are like crash handlers and things like that. But the hardware interrupts are driven by hardware peripherals, And they will throw in the OS tick timer as a hardware interrupt also, although on certain CPUs that's kind of hardware and kind of software. But usually but going back to the hardware interrupts, the interrupts are configurable because you've got a variety of peripherals on any type of CPU, and then you've got external hardware in that, whereas the software interrupts are part of the CPU design and are the same on every single vendor chip. So what must an RTOS do with respect to exceptions? And since this presentation is about what the minimum features are for an RTOS, I am qualifying these minimum features with respect to exceptions. So first point here, a hardware ISR must have the capability of making kernel API calls. If you don't have this capability, you are not an RTOS, and this separates schedulers from RTOS. As a hardware ISR kernel API call has direct context, say direct processing between the ISR and a task starting. So the important thing is when you make a kernel call from the interrupt handler, that kernel call actually, depending on the RTOS, won't actually start until the ISR is complete. But the point is that when that ISR has completed, you will immediately start the kernel running, and then the kernel will process that request, and if that request results in a context change, a context switch, a preemption, or just the scheduling of a task, if the system isn't running any task, then that must happen directly. That must happen through a direct series of steps where there's no sort of forced waits, pulling on hardware, or something like that. So here's a picture of this. You've got task A running, and a task will run independent of any type of hardware interrupt. In other words, hardware interrupts, and here I show it on the second line here. And by the way, this diagram shows time increasing from left to right across the horizontal, the x-axis. So task A is running, minding its own business, so to speak, and some hardware event happens. There's something electronically which tells the CPU to execute this ISR. And this is all has nothing, that doesn't have much to do with the RTOS, doesn't have anything to do with it. If the ISR is configured, when the hardware event happens, it will stop this task, and it will switch to this other thread, the task A being a thread, task B being a thread, ISR A being threads. ISR A is not a task, but the ISR A gets scheduled. Well, scheduled isn't the right word because that applies to task. The ISR A will run and break task A right at the end of the last assembly language instruction, like I said before, that was executing. And tasks, when that happens, task A's context cannot be corrupted or altered. And the way the RTOS does this is it works in conjunction with the features of the CPU to accomplish this. So it'll be done partly automatically by the CPU and partly by the kernel, and it can be deferred, but that's a different, all this is a different discussion. ISR will run, and it will not use a lot of the CPU probably. When it finishes, let's just say in this diagram here, it made a request to the kernel to schedule task B, and task B is at a higher priority than task A. So when ISR A completes, the kernel takes the CPU for a bit, and it saves A's task context and puts in task B's. So now task B is running as a result of this ISR. When task B blocks, then you go back to task A, because task A, which is the one which was previous running, assuming there's no other task at a higher priority that wants a CPU. So there are also, so what I said before are the minimum features an RTOS must have to be called an RTOS with respect to exceptions. Here are some nice to haves with exceptions. Having an OS tick. Now, RTOSs do not have to have an OS tick. In fact, OS ticks are not good if it's a battery system, but an OS tick allows you to have API calls which have timeouts and other features that the kernel can support at the API level. But it's very nice to have a software interrupt to support that trap mechanism to enter into the kernel. And you can use that. So most people, who port an RTOS over to a CPU that has this mechanism, will use it. Now that's not I don't put this down as a have to have. I've seen RTOSs which don't use these traps, but most people that implement OSs like to have them. And it's also, along with that trap mechanism is software interrupt for context switching. Say in the case of an ARM Cortex CPU, let's call this PendSV. If you understand that CPU, that'll make sense. But these first two categories, I'll just combine them into the same. They're both software interrupts, which are callable from the application or kernel. Startable, actually. Now, the last category here is software interrupts which support low-level crashes like bus faults, illegal instructions. In the ARM architecture, you have usage faults, memory management faults. These things are crashes. So if you don't have these software interrupts and a crash occurs, then you might not find out immediately. You'll probably find out eventually, but you won't have the benefit of knowing immediately when this happens, and this will make your system more difficult to troubleshoot. But it's a nice to have, and it's not a must have. So let's look at these things individually. Like the hardware timer, an RTOS OS tick will have a hardware timer, and that hardware timer will drive an ISR once every n milliseconds, so many times a second, whatever. It'll be spaced at the exact time interval every so many milliseconds. So this time interval allows application code to get some sense of time. So in NUFR, this is used, and NUFR is typical of uses by RTOSs. NUFR will use a hardware, this RTOS OS tick to allow, like I said, timeouts on API calls, but also it can be used to hook into to build your own timers, so that you can have a callback after so many second delays or something like that. So the application code can if it's turning on a light on and off, it can say every 10 seconds have a timer call it back, so that it knows to toggle that light value. Next thing is if you have a battery powered device. Obviously, in a battery powered device, this system is not going to be running very often, or you'll deplete your battery. So in a battery powered type of device, it can be anything from a key fob in a car, a Fitbit, a remote control for a television set, anything that's battery powered. is not on continuously, or that battery is going to wear out in a matter of hours or a few days. You will use the CPU when you need it, and then put the system to sleep to conserve power. So you can't, if you use an OS tick in this case, unless it's really slow, like just a few times a second, like maybe in the kilohertz range, then you will wear out your CPU, because even if it's, I'll scratch that last statement, that in that kilohertz range, that's only a hardware timer inside it. If you'd actually handle OS ticks in a kilohertz range, you'll quickly wear out the battery. So unless it doesn't make sense to have a really slow OS tick rate. So in a battery system, you won't find OS ticks. Other RTOS features. Only hardware interrupts can preempt a kernel API call. Now, these features are when you need a more advanced CPU to have the capability of having different interrupt priority levels, which is something that your more advanced CPUs can handle. You might want to have some of those hardware interrupts interrupt kernel API processing, because kernel APIs can take a relatively high amount of time compared to an interrupt from hardware. The kernel processing is a critical path for context switching, but it's not a critical path with respect to certain hardware interrupts. This gets complex, and this, of course, is explained in NUFR. Go get yourself a download copy of it and start poking around the files and the documentation, and you'll see how NUFR does this. So a kernel is not going to block for hardware events. And all these things that I'm stating here are, again, minimum requirements for an RTOS up to a point. You don't want the kernel off trying to read when a hardware event happens. You could probably get away with implementing an RTOS like that, but it's not going to be. It's going to have limitations. It's not going to be the sort of RTOS you want on any sizable or any system which is a mainline system powered by mains powers. Your kernel must execute in atomic calls and not have some sort of a trick under the cover where it's sitting in a loop, running around, waiting for this or that to happen. The kernel's going to be ready for anybody that needs to use it and not block off interrupts all the time. An RTOS must, of course, as I said, must allow kernel calls from the hardware interrupt ISRs, and as I've discussed before, this chain of events must be direct. You've got certain types of operating system schedulers and that where an ISR happens and it sets a flag or something, and then when the ISR terminates, you've got to wait for the next poll interval or something like that for the kernel to pick this up, instead of directly entering the kernel after that ISR has completed. And these bullets I've covered before. I won't repeat the details of them. Another feature to an RTOS is that it must have an API interface for applications, which is basically the codes which runs at the task level. So this API interface, as I've said, must be for both applications or task level code and ISRs, not one or the other. The kernel API behavior must stand up some sort of a contract which should be enforced, must be enforced according to the documentation at all times. This is true of all OSs, but in an RTOS, the extra requirement over an OS is that these well-defined behavior also include timing. So in other words, if you have an application or something which makes a kernel API call, you can't cause the kernel to go in and hog the system for an inordinate amount of time and thus violate timing constraints. Other OSs, though, when you make a kernel API call, they could lock out the application code for a long period of time, say longer than several microseconds. In that case, they violate timing constraints and they are not an RTOS. This is a big distinction between what makes an RTOS versus just an OS. So this is where all these points are brought up come to a point, come to focus. This kernel API calls executing directly. If they don't execute directly, then you get into these situations where the timing constraints aren't met. Directly, as I said, excludes spinning on a hardware timer, pulling a device like an I/O device, waiting for a disk read to complete, waiting for some value to come back over a serial line or an I2C interface or something like that. If the kernel is doing this, it's going to cause real-time problems. Now, it's a different story when your applications and your interrupts get into pulling loops and they cause problems with other applications. That's not a problem with the RTOS. That's a problem, the real-time problem with the design of the applications and the drivers and all that. But the RTOS must not get its hands dirty doing this stuff. And to clarify what an atomic API call is, it's when you make an RTOS API call, it will run through to completion, and it will, for a short period of time, complete atomically. In other words, it won't be in its of itself. The kernel will not be preempted by another RTOS API call. So the state of the RTOS is completed in the single API call without being disrupted by another API call. If a second API call occurs while the first one is happening, it gets basically queued waiting for the first one to complete. So you serialize completion of all the RTOS API calls. And all operating systems do this. I say all of them. Some of them are, you get into more sophistication when you talk about larger operating systems, and they'll do all kinds of fancy things. But to suffice to say, an RTOS API call is not reentrant or recursive. And again, go into the NUFR literature to see what reentrant means. And even down to the ISR level, this constraint must be held. And this one makes RTOS designs tricky, makes them run a little bit slower than schedulers, is that you got to make sure that all of these contracts are satisfied across all the different use cases. But the ISRs, although they can interrupt the kernel and do something, they will not interfere with what the kernel is doing. So those are all minimum features and a few nice to haves. What are some of the more sophisticated features of an RTOS? So the RTOSs which run with memory management units like QNX, Neutrino, same thing, Neutrino's the later name for QNX. That's RTOS does take advantage of the memory management unit and runs POSIX type threads and things that you find on Linux, and at the same time is able to adhere to the real-time constraints of what an RTOS must do. But for the most part, when you go and Google the word RTOS, you will see that you're talking about a single core, non-memory managed type of OS and programming environment. So, as I've said in the last presentation, the term RTOS is overloaded, means a couple of different things, but for a operating system to be real time and not the prevalent Google definition of RTOS, it can still take advantage of a memory management unit and all the separated addressing spaces and the protection that you have at the process level. So with a MMU, you can then implement processes and get the stuff that you get on the Linuxes and the Windows to work your RTOS. And some RTOSs have extra features which are integrated into them. I didn't include any of these extra features like file systems, device drivers, protocol stacks. On some RTOSs, this is an important capability that they offer, and they will advertise it because it's a feature that is attractive to a lot of their customers, but not something they would list as an absolute essential to call something an RTOS. And there's different architectures for this. You can have file systems which are bolted onto RTOSs. You can have file systems as a part of an RTOS. Same as with various device drivers and protocol stacks. But these nice to haves on large systems are very nice alternatives when you need them. And but a lot of times the architecture is such that these bolt-on features are not part of the RTOS. However, they are packaged together with them, bundled and sold under the same licensing agreement or something like that, or they're made to work. You have a file system that's made to work with a particular RTOS. These are a large part of some of the larger RTOSs out there on the market. So I will get to the difference between an RTOS and a scheduler. I started touching into it on this part. In the part 5, this is something that a lot of people, when I get into this distinction between a scheduler and RTOS, you can start to get some disagreement here. But I think up to this point that we will have a lot of consensus. So hope that you come. I hope that you listen. Come out and go to YouTube and watch the part 5, and I will include getting onto the more advanced features that an application would use in an RTOS and how to set up applications. I'll cover that in some other parts as we continue to get deeper and deeper into this. But you won't want to miss it. And I hope to see your likes there on YouTube. We'll see you then.